Okay, maybe we started because several words before I would like to say you, dear colleague, I'm very glad to welcome you to our session. Thank you very much for your attention to this problem of the observation, multi-messenger observation of the relativistic stars. I mean the very, very fast variable object in our very powerful and variable object in our universe. Okay, we have the 7 speaker, and first Franco Giovanelli, Professor Franco Giovanelli from Roma. Nice to meet you in good faith and good health. I'm very happy. Can you start your talk? Okay.
Thank you. Okay, good morning to everybody. I would like to present an example of multi-frequency behavior of one high-mass X-ray binary system, which is the best studied since its discovery in '75. A few words about the line of the talk. The talk is based on the review papers by myself and Lola Sabao-Graziati and myself, just about X-ray binary systems. This is the outline of the talk, and the introduction is very simple. We have this slide, which for most of us is completely ununderstandable. This means that the truth is written in the book of the nature. We must learn to read this book, simply. The universe manifests not only through electromagnetic radiation, but also through astroparticles, including neutrinos and gravitational waves. The zoo of X-ray binary system is the following: high mass X-ray binaries, low mass, cataclysmic variables, RS canum venaticorum, anomalous X-ray pulsar, and soft gamma ray repeater. And in this slide, you can see also the energy emitted, in the range of the energy emitted for each kind of this class of objects. X-ray binary in the Milky Way are distributed along the galactic plane, and mostly, especially the low mass X-ray binaries, in the center of the galaxy. This is the 4th IBIS catalog, in which are reported the AGNs, high mass X-ray binaries, low mass X-ray binaries, cataclysmic variables, and unknown objects. High mass X-ray binary systems are divided essentially into subclasses: hard transient X-ray sources, in which we have a B-type stars, and the eccentricity is rather high, and the permanent X-ray sources where the eccentricity is almost 0, and we have OB-type as an optical companion. They transfer mass with essentially with the wind fed, sporadically with the disk fed, and both contains X-ray pulsars, and the magnetic field is of order of 10 to 11, 10 to 13 Gauss. Anomalous X-ray pulsars, optical counterpart probably exclude OB and the B star, and the magnetic field can reach up to 10 to 15 Gauss. Supergiant X-ray binaries are formed by early type supergiant and the weakly magnetized neutron stars, and the accretion is usually via stellar wind. The supergiant fast X-ray transients have this peak energy in X-rays 10 to 36 erg per second, and quiescence 10 to 32 erg per second, probably wind clumps on the accretion disk and a wide orbital neutron star. These systems are formed by a compact star and an optical star, and obviously there is a mutual influence between the two stars. And this means that low energy processes influence the high energy processes, and vice versa. X-ray transient sources is a subclass of high mass binaries and show multi-frequency behavior which deserve particular attention in order to understand the causing physics. This is I will present a short history of this system, which is the most studied system since its discovery in '75. And I can show you that through the multi-frequency observation, simultaneous or not simultaneous, to solve a lot of problems of the physics governing such a system, which is a prototype of this kind of objects, then we can generalize to all the other X-ray B systems. The discovery of the X-ray transient source of 535+26 happened by Ariel 5 satellite in '75 April, and these are the counts detected by Ariel 5. The discovery of the optical counterpart, how we reached to the discovery of the optical counterpart. Margon et al., using the error box of the Ariel 5 satellite, found one B star 9th magnitude in such a field, and the probability to find one 9th magnitude star in such a field is very low, 0.004. That's probably suggested that this is probably the optical counterpart of the pulsar. But in order to have the security, it's necessary to have simultaneous measurements in optical and X-rays. And I put in a diagram the X-ray flux intensity measured, the first burst, the second burst, and we had few points here in red. So I constructed the hypothetical light curve like the first one, and the hypothetical second burst. Then it was the predicted outburst was in this range of dates, and we were waiting for optical measurements. We did, and we discovered the correlation between the pulsar and the optical star. Then the HDE 245570 is the optical counterpart of the pulsar. The classification of the star happened with all the Kodak 103 AO plates. Only all the people present here probably remember, because we had not a CCD camera, we have not the new technology. And in spite of this, we recognized the 139 lines, and we classified this star as 09.7 third class of luminosity. This classification is still working after 41 years from our paper in '80. Multi-frequency non-simultaneous observations allow to solve the mass flow rate, spin up of neutron star, etc. Then, using our measurement from ultraviolet to optical to infrared, we determined the mass loss in 10⁻⁸ solar masses per year in quiescence, and roughly 10⁻⁷ solar masses per year in outburst. Using the pulsed period of the star, it was possible to determine P dot over P in -6.8 in 10⁻⁴ years -1. The cyclotron high energy magnetic field in the pulsar. This was a list of made by Corbun in 2002, and now we have an updated list containing 27 systems, and the energy of the cyclotron line of the star was 46.3 keV, giving a magnetic field of 4 in 10 to 12 Gauss. These are the ultraviolet measurements. Then, feeling the 2200 angstrom bump, it was possible to determine EBs minus V equal 0.75. from the broadening of the symmetrical line helium-2, it was possible to give the rotational velocity multiplied by sinus of the inclination angle 230 km per second. Later, it was possible to determine the angle 57 plus minus 2. And from the asymmetrical lines, carbon 4 and silicon 4, it was possible.
Я сижу на конференции, вы давно приехали, я на конференции уже сижу.
Sorry?
Конечно.
It was possible to determine the terminal velocity of the stellar wind. It was possible to find also the indication about the temporary accretion disk around the periastron passage. Then we have one idea looking at the event occurred in December 581, marked in red. We had enhancement in UBV light curves, and we suggested to Acuccio team to look at this source, and 8 days later it was we had an X-ray outburst using p-orbital 111 days that in agreement with all optical and X-ray determinations. Myself and Bisnomati Kogan and Klepnev determined the ephemerides of this object starting just from this event, and using this ephemerides, we look at the optical data, optical and X-ray data, and the X-ray data around the passage at the periastron. And these are optical data at the periastron without X-rays. You can see that we have several measurements practically at the periastron. And these are optical and X-ray data around the periastron. You can see here the optical, here the X-rays. And this is another example which gave us the possibility to suggest the X-ray event, of course, 8 days in advance that it occurred. And these are another example for which we had also the possibility to predict the X-ray outburst. And this is the last we have at 122 cycle after the event of 81. Then these are the measurements at the periastron without optical data, only X-ray data. And using this ephemeride, going back to the discovery of the Ariel 5 satellite, the discovery of the pulsar by Ariel 5 satellite, we see that the periastron is just roughly 12 days before, but the Ariel 5 satellite started here. So this periastron passage is compatible with the delay of roughly 8 days between the passage at the periastron and the start of the X-ray outburst. We have a relationship between X-ray intensity and the delta V magnitude, which is a good method to predict through the variation of the relative variation of magnitude in optical to predict the intensity of the X-ray outburst. Therefore, we developed an accretion disk, a geometrical thin and optical thick without advection, a model. From the B star, the matter entering the outer part of the accretion disk. Because accretion disk is viscous, the matter needs some time to go to the neutron star. And in the case of this source is 8 days. But this was already showed by Smack and Lasota, for instance, that we had ultraviolet and optical delay in the case of cataclysmic variables. Therefore, this model can be generalized to each kind of objects in which the accretion occurs via accretion disk. Then, looking at the formula derived by this model, this is the time delay, in which m is the mass in solar masses, m dot is m dot in 10⁻⁸ solar masses per year, and T4 is the temperature in optics in 10⁴ Kelvin, and alpha the viscosity. We used this formula to verify for different class of objects the validity. And we used the B X-ray source we discussed until now, SS Cygni, which is a cataclysmic variable, Aquila X1, which is a low mass with the neutron star, and GRO, this one, which is a low mass X-ray binaries with black hole. These are the experimental delay, and these are the calculated delays, which are really in very good agreement with the experiments. So this model is very, very good, very powerful. This model, however, is not valid in the case of active galactic nuclei. We have these delays measured for a sample of galactic nuclei. Then it is possible to see another possibility to explain this delay for active galactic nuclei, which is the tidal disruption of a star by massive black hole. Appeared in 1975 a very interesting paper in Nature by Hills, in which a star approaching a supermassive black hole with field increasing strong tidal forces. Once the self-gravity of the star can no longer withstand those forces, the star is ripped apart, and this happens at the tidal radius given by this formula. Only a fraction of the stellar material will eventually accreted, while the remainder is unbound and escapes from the system. The bound stellar material follows Keplerian orbit of a high eccentric and returns to pericenter at the rate the m and the t proportional to t minus 5/3. And then a star which passes too close to perturbing potential will be disrupted. And this is a sketch of what is going on around the massive black hole. This is the stripped star. And these are experimental data from this object coming from Swift and XMM Newton observations. We can see this light curve. This is simply with the logarithmic scale, so it is much better to see this decay. And this decay is just with the t to minus 5/3, just predicted. And this is another example. So we developed the model of a time lag formation in AGNs, and I jump several slides. We can say that the tidal disruption leads to the optical flash, and the X-ray flash starts when the matter of the inner jet is sufficiently heated to radiate in the X-ray region. The radius at which the optical flash occurs is calculated for the motion with the free fall velocity as this formula, and taking tau ff equal to tau observations, we obtain a radius of the optical flash as this value, where t observation is expressed in days and the supermassive black hole mass in solar masses. With this, we can add that a tidal disruption event occurs when the tidal force from the supermassive black hole Ft becomes comparable to the gravitational force of the star Fs. And in this case, we can express these values like this. Using this formula, we obtained, for a sample of active galactic nuclei, for which we have tau observed, the delay observed experimentally, and we computed the R optical equal to RT and the radius of the star in centimeter. Just to prevent the question, however, we note that another possibility to interpret the short time delays in AGNs is based on the irradiation model, like suggested by Ulrich et al. And this model could explain recently extensive observations of these galactic nuclei in X-rays with and ultraviolet and optical light made with the Hubble Space Telescope in the reverberation mapping campaign, so that we have another possibility to explain this delay. But however, with our formula, we justify the experimental time delay between optical and X-ray flashes observed in AGNs. So thank you for your attention. You can
Thank you very much, Franco. Very, very impressive talk. Unfortunately, not enough time for you, because I know you can give a more wider object, but very good, because the accretion relativistic stars is one of the classical type of the relativistic star, neutron star, for example, but genetically connected with young neutron stars like magnetar and old neutron star like to millisecond pulsar. That is the whole zoo of the relativistic stars in our galaxy. And is there any questions, people?
I have a remark to make. It is necessary, in my opinion, to deeply measure several kind of objects in order to understand the real physics governing them. Because if we have only measurement, sporadic measurements, it is very difficult to understand the real problems occurring in these systems. This is the reason because I showed you the very deep measurements of this X-ray system I have presented.
Yes, yes. People, is there any questions? We have time because we have not a lot of speakers, but
yes.
Several questions maybe.
So I have a question, Franco. Are there any predictions for electromagnetic emission if a neutron star in a, say, one of the example binary systems you showed would accrete enough matter such that it would collapse to a black hole, so it would be over the neutron star stability limit and would collapse. So are the accretion rates and the time scales viable for that to happen, and are there any predictions about electromagnetic signatures for collapse of a neutron star in such a system?
I think that we have to look always at the low energy emissions, because starting from the optical emissions, we can have information about what is going on the accretion disk, because very often people start to look only at the X-ray measurements, forgetting completely about the origin of the X-ray emission. The X-ray emission is originated by the optical emission from the companion star. Therefore, it is necessary to have both measurements possibly simultaneously. Only this is the method to understand it. Otherwise, we can always make some speculation.
Thank you very much. Is there any important questions? No. Okay. Next talks. My talk. I would like to start. Can I take my demonstration? Это установлено. Just a momento. Это установит демонстрацию экрана. Ага. Демонстрация экрана. Just a moment. Вот так. Okay, you see, and my talk, people. Franco, all okay? You see my talk? Aha, grazie, grazie. And listen my voice.
We see both the slide and the voice.
Okay, very good. Today I would like to give the small talk about the very concrete model of the one of the brighter gamma ray burst of the 21st century, the 160625b, and this famous very bright optically and X-ray and gamma ray burst. For example, in optical we see the 8 magnitude optical magnitude we see by master system, and we detected this object before the beginning of the main pulse in optical. And so today I stress on the prompt optical X-ray and gamma emission of this gamma ray burst, and I would like to explain these properties, the properties of this type of black hole formation during the very fast rotating gravitational collapse. That is my co-author of this work, and here you can see the real image. You see real image here. That is a light curve. There's an optical light curve detected by master for especially not big telescope, only 7 centimeter very wide field camera. This point is 7 centimeter very, you see this magnitude very bright. And the first, here our main telescope detected polarization and published it in this paper several years ago. But when I look to these events in optical, you can see that after 17 seconds, you see they appear some quasi-periodical pulsation. Not very strong, but if you have some experience in the light curve, you see the sometimes with not very determined, very strong period, but quasi-periodical pulsation. And in this paper, we think this pulsation connected with formation gravitational bounded object, not neutron stars, but more complicated object like to neutron stars, but which hydrostatic equilibrium is maintained by 3 forces. The centrifugal forces is very important, the gravitational forces, and nuclear pressure of the nuclear matter of the quasi-neutron stars. This object we call the spinar object. Maybe later I show you. But what about observation? This in first paper we published the polarization, our result, and analyzed it. with Fermi Swift and Fermi Lat observation of this. Here we presented the first presented the Conus Wind and Lomonosov gamma observation, and two telescopes in the Crimea and Canary, the optical observation in the light curve, this light curve. You see here our observation started before this main pulse, about the 150 seconds, because before this here the Fermi GBM detected the bright precursor. Okay, and so the first point we proposed that after 70 seconds formatted. Here you see the light curve is changed. Here you see this very bright and so, and here the another power law index, and we explain this by formation of the spinner. So, okay, there's another picture. I would like to stress your attention to the three main points in this. That is the observational time, the redshift about 1.4. So the real in the rest frame you have the 2.5 shortly, but this is the observational time, and you see the first event is the precursor. The second event, main pulse, very, very bright main pulse, G2. And the next one, the last one, starting from 400 to 500, G3, some brightening image. Very interesting that, for example, this Fermi-Lat, this schematically you see Fermi-Lat do not observe this event, only some very small extended brightening, but that is a light curve receiving by Lomonosov, Russian Lomonosov satellite. This is some type of observatory with optical and gamma ray telescopes. And you see here, that is very interesting that even G3 most successful observation was done by Lomonosov, because another, for example, Conus Wind, very good, nice observation here, but here more or less not sensitive, but not very good statistics. But in any case, we have the synthetic all we see all by Conus Wind and Lomonosov, all three main events from during the 700 seconds in observational systems. Okay, how to understand? That is a Lomonosov orbit, and you see the Lomonosov do not see main pulse because it moves through the anomaly, a lot of background of the cosmic, the particle, relativistic particle and the cosmic particle. And so, but here you see very, very nice light curve for the even G3. We tried in this work, we tried to explain all these three events. That is Conus Wind, very good data. You see the central part, very interesting, very data. That is the main pulse, very bright. And very interesting. That is, for example, you see that is the IP Conus Wind team, our co-authors of this paper, found the put on the general diagram of the peak luminosity and ISO energy, and so you see this main pulse is here, is very bright, and the precursor is more or less two order less energy. And here, that's very important. We found, we analyzed of the in this case, multi-wave observation from the optic, this optic point. I'm sorry for this very small point, but you see the common spectrum, that is the time, and you see the common spectrum appear only here, this more or less good. You see optical and this gamma ray spectrum. Here, gamma ray spectrum in first seconds of the prompt observation, this real prompt observation, you see no common spectrum, but common spectrum appear on the 70-second. Yeah, I remember you that at the 70-second, the light curve is low, is changed. So we will connect it with formatted the gravitationally bound object, not black hole. That is demonstrated the power law light curve through the time. You see 70 second is very important, very dramatically changed of the power law of the light curve. And what happened here? We proposed our model, which really grows from the 16 years from the idea Hoyle, Fowler, Rezernoy, Moritz, and here you find some story, but people discuss it here the supermassive stars, which equilibrium maintained by not only the hydrostatical pressure and the centrifugal forces, very fast rotating, and Oestreicher and me proposes that this stage during the collapse can reappear during the collapse of the usual stars to black hole, the stars mass black hole. The Lipunova, by the way, gives a relativistic spinar first consideration. Okay. What happened? You see here that is a pre-collapsed progenitor. The collapse, the core of this core is very fast rotating due to, for example, synchronization in very short binary system. And after loss of stability, this collapse is started, and the first event G1 is a precursor when the centrifugal forces stop at the collapse and first, and this formation of spinar. That is the approximate very quality formula like to Newtonian, which we generalized on the general relativity later. And so you see, we in this paper we proposed the all fast rotating magnetic rotation collapse have minimal two-stage first formation of the spinar, fast rotating body, with very important rotational centrifugal forces. And after the magnetic or viscosity dissipation of moment, this spinor comes to the black hole or neutron star. You see this scheme. So we have two-stage collapse. And we explained the well-known phenomena in the gamma ray bursts, the plateau. You see two plateau. Now we know a lot of plateau, but some plateau show us the very, very dramatically several orders decreasing gap, not decreasing, disappear of the gamma ray and X-ray emissions. And this very long plateau, 10 to the 4 seconds, 10 to the 4, 10,000 seconds of the, you see our model explained this plateau as the evolution of spinor energy. You see spinor dissipative of the angular moment, but usual neutron stars is the energy, the luminosity is decreased, but in spinor increase, slightly increase, you see here. But after the collapse, you have the disappearing of all X-ray emission. And you see afterglow against this afterglow, this afterglow, as this. Okay, this model we proposed very simple, not very simple, but differential system of differential equation, which included all relativistic effect on drag frame effect, gravitation ratio, nuclear matter pressure, relativistic magnetic field, and disappearance, relativistic magnetic field disappearing, black hole no hair, and magnetic spin down. And you see here we calculated all the collapse up to the zeta, the radius in the gravitational wave, 5 gravitational wave in real time. And you see this rotation and dissipation by magnetic field, as this luminosity slightly increased, and after that collapsed and a higher ratio gravitation. But for this gamma ray burst, which we especially considered in this work, we proposed that the mass of the nuclear is very close, not very big, and close to the Oppenheimer-Volkoff limit. In this case, after the formation, you see this, the precursor is the formation of spinor. And second, that is the main pulse of the very formation of the very higher formation object like to spinor all magnetar, not magnetar because magnetar spin down. This is spin up. This now object spin up during the evolution, and this spin up with higher magnetic field, slightly dissipating magnetic angular moment, and come to the this fact formation, the spinor, which equilibrium is maintained by not only centrifugal forces, but nuclear pressure, because Oppenheimer-Volkoff limit is very close to this nuclear, to the core of the collapse. And in this case, this very important case, because well known, the Oppenheimer-Volkoff or the fast rotating neutron stars must be about the 5 or 6 solar mass, for example. So this not collapse. This spinor magnetar, some mixing spinor really must be loss of moment and formed black hole. This G3, which detected by Lomonosov. You you see here the data of our models and explain it all typical time of each moment and typical energy. This fluence during these events, you see precursor 2% and even G3 is 10% and this 90% main pulse. That is our model. Here you see that as an observational scheme and gamma and optical and so. And you see here that is formation spinar, pure spinar. And after this moment, at this moment, maximum connected with formation, with growing of the nuclear forces of the nuclear matter of neutron stars. After that, luminosity is decreased. That is the radius calculated up to the less than light to gravitational radius, and for the Kerr metric. And this magnetic field is very big. Unfortunately, this is about 10 to the 15 Gauss at the maximum. And you see magnetic field of the formation spinar is grows up to the relativistic effect of the magnetic field disappearing here and magnetic field come to zero. So the qualitative model explains this all three events of this. Thank you very much. Also, is there any questions you can ask me? Short, because maybe I use it slightly more, but we have 5 minutes more for each talk we have.
Okay. I would ask about the mechanism of last GLB event formation. We understand that gamma quanta appear due to Bremsstrahlung from relativistic electrons, which can be ejected from the central engine. But mechanism of formation of jets when spinar collapse in black hole and when progenitor collapse into spinar are the same or not? Mechanism of jet formation in the stage G3 and G.
Yeah, G3. You see, here we have the very, how to say, we have the very massive neutron stars, 3.5 solar mass, but not collapsed only due to the fast rotating. The fast rotating neutron stars have a very big Oppenheimer-Volkoff limit. This is well-known fact. But really, here we include this. If you include the centrifugal forces, this very understandable. So, after the dissipation of the rotation spin moment, the Oppenheimer-Volkoff is low, and when it lows and the mass of the core G3 is the real collapse to black hole, and this last third bright, more or less bright, not very bright phenomena in this very interesting collapse.
But what is the reason for magnetic field dissipation? It is due to jet formation or not?
No. Magnetic field dissipation, that is a well-known Penrose theorem of the, because the black hole have no magnetic field.
Only because the black hole
no hair, black hole will have no hair. That is a well-known mathematical theorem from the 16th years, last century. Okay, thank you very much. We must listen the next very interesting talks by Stefan Smart. He is well-known researcher of the transient of the Implant Star project, and very nice active participant of the gravitational wave. All very interesting last 10 years astrophysical experiments. Okay, Professor.
Vladimir, could you let me share
you can
the screen?
remove
Excuse
you can
me.
remove the screen.
Yes, please.
Ah, I see. Can you take screen?
Yeah, it says you're still screen sharing. So I can see your screen. It's not PowerPoint, but I can see your screen. If you
Okay,
okay. Okay, that should be fine now. Yep, got it.
Okay, you can take. Oh, nice.
Okay, let's see. Can you see my screen? Okay.
Yes, all okay.
Yep, good. Okay, so thanks for the invitation to speak, Vladimir. I'm going to talk about searching for merging compact objects and their electromagnetic signature in wide field surveys. And this is implications for multi-messenger astronomy, particularly gravitational wave detections. And I work with various surveys that I will talk about, that I'll mention. So in 2017, the famous kilonova was discovered, the gravitational wave source 170817 from a pair of merging neutron stars with a long signal lasting about 60 seconds was discovered, and at the same time, or less than 2 seconds later, around 2 seconds later, there was a short burst of gamma rays detected by Fermi and Integral. So for the first time, we had a detection of a electromagnetic signature and a gravitational wave temporal coincidence. And the sky map was small enough that just within 11 hours in the first night that the area of sky was visible from Chile in this instance, then there were 8 telescopes in total, but six optical telescopes observed the optical counterpart before it was announced it. They all worked independently. There are actually 8 detections on the same night, but 6 certainly worked independently and detected the counterpart in a galaxy NGC 4993, relatively close, only 40 megaparsecs. And there's the master image in the bottom left there, led by Vladimir. So this confirmed this was confirmation of the electromagnetic counterpart. The area of sky was guided by the gravitational wave, by the gamma ray burst detection, but it was really the gravitational wave map that reduced the sky area such that some of these telescopes actually selected the galaxy. Some of them, like Maestro and DECAM, were capable of tiling out the whole sky area. But very exciting, of course. And after that, every telescope in the world then pointed at this particular object in NGC 4993 and found it to decline very rapidly, unlike any other optical counterpart that we had ever discovered. Really, this was completely different to any transient that we had found in the universe. So here's an image. On the left, you can see a bright blue source which pops up at the northwest of the galaxy, and it turns red quite quickly and then fades away. And the image on the right is the light curve. So this peaked at a luminosity of around 10 to the 42 ergs per second, and then faded very rapidly over a period of about 10 days. So to get to that luminosity within 11 hours of the merger, requires a very large velocity because the material has to expand a photospheric surface that will emit radiation at the luminosity of 10 to the 42 ergs per second. The early radiation had a thermal black body spectrum. So to get to that photospheric radius, it needs to be moving at about 0.2 C to reach that radius. The total ejecta mass was estimated by several groups. I just list the parameters that we estimated at the time of the event, but more or less this was an ejecta mass of about 0.2 solar masses. maybe 1% of the total mass of the merging neutron stars was ejected. And if that's ejected at this velocity, and depending on the opacity, then various groups have estimated the opacity of the material to be quite different. But fundamentally, this can be explained by a low ejector mass, which is heated by radioactivity. And the radioactivity powering law is it's just a power law, and that encapsulates the powering by heavy elements, or process elements heavier than iron. So if you add up all of the powering by those radioactive elements, you get a power law with an exponent of around somewhere between -1 and -3. And this is a simple model shown here, and that does a good job of reproducing the luminosity. So very exciting discovery. Since then, though, so this is the only one we've ever discovered where we've got a gravitational wave signature and an electromagnetic counterpart. It's also the only clear detection of an electromagnetic signature. We call this a kilonova because it's about 1,000 times brighter than a nova. So it's the only. There are some hints this type of emission, and effectively this is thermal emission from the radioactive emission being thermalized. There is some somewhat ambiguous evidence of this happening in short gamma ray bursts, in very nearby short gamma ray bursts. So in GRBs, as we saw in Vladimir's talk, of course, the afterglows are very bright. If you observe some short GRBs as the afterglow fades, there's a hint in some that you have a thermal signature late in the afterglow or after a few days. But they're not clear. I think it's fair to say we do not have another example like this, a clear detection of a kilonova. And we've been searching for electromagnetic counterparts over many years. Many wide field surveys have been searching independently of gravitational waves for fast declining transients. So what we're doing and what other groups are doing now is trying to find objects like this without gravitational wave signatures, because they should be there irrespective of the gravitational wave detection. When LIGO and Virgo and Kygra are currently off, these events are happening in the local universe. This was 40 megaparsecs. So these are clearly merging neutron stars happen in the local universe. How frequently they happen is not certain. The rate of these events is not yet certain, but I'll come back to that. But they should be happening, and we should be able to. This is 10 to the 42 ergs per second, absolute magnitude of -16. These are not difficult objects to find. They're similar to the luminosity of faint supernova that we find in the universe. So we should be able to find these electromagnetic counterparts without the gravitational wave signature. And so no one has found out any yet. Here are 64,000 transients registered on the transient name server, the IAU name server. Currently, the place that we register our public detections. These have been detected by our group, PanSTARRS, ETF, Gaia Alerts, Master, Atlas. And so these are just everything up until the start of this year, 64,000, but none of them have been confirmed to be anything like a kilonova. So this is what we are searching for signs of merging compact objects. And these are virtually all supernovae. Some of them will be confused and be galactic objects, but virtually all of these are supernovae or supernova-like transients. So we're searching for things that are nearly as bright as supernovae, but fading very rapidly, which implies a low mass, which likely implies a compact star which produced them and potentially a merger. So we do this. I personally do this with 2 telescopes in Hawaii. So Hawaii and Ireland, where I live and where I work, is a perfect longitudinal match, because as Hawaii is observing during the night, then we can work during the day, and we can process the data here during the day while Hawaii is working at night, and then search. Because these objects fade rapidly, we wanted to find them as quickly as possible, combine them with any other data that's available, like the ZTF public stream. And so there are 2 facilities in Hawaii, one the Atlas survey and the other one the PanSTARRS facility. Process both of the data in Queens now. So our computers are now running and processing the data that the Hawaiian telescopes are now producing. So we've not like Maestro has got a better longitudinal coverage, of course, on both hemispheres as a comparison. Although we will put 2 Atlas units in the southern hemisphere this year for full sky coverage. So we've been looking for these, particularly with Atlas, because Atlas has all sky northern, covers the whole northern sky every 2 nights to a depth of 19.5. So we process the data here. We will be putting 2 new telescopes in the southern hemisphere this year, Chile and South Africa. We also make our data public. So if you can go to our force photometry server, if you have a position on the sky, you can go to the force photometry server, get the measure photometry at the position of your object and check if we've any signal. So we also observe 4 times per night, because that's because the primary mission is to find near Earth asteroids. And we observe the sky. If the weather is good, we can get around the whole northern sky every 2 nights with these 2 telescopes that we have in Hawaii. Each telescope has a 30 square degree, 29 square degree camera, and it's a 0.5 meter telescope. So we hope when the southern telescopes are commissioned, then we'll have full all sky every night to 19.5. And again, we'll release our data, our discoveries, but also we'll allow people to do measurements on all of our data publicly. So we have been searching for all transients we release publicly. We've been searching for kilonova for the last few years. We have not found one kilonova candidate, and no one else has found a kilonova candidate. But we can set an upper limit on the rate of optically bright kilonovae. And here is our current rate. So this was done by my PhD student, Owen McBrien, who's just written up his PhD. And this is a paper in preparation that we have. So both ZTF and Atlas have produced an upper limit on the rates of kilonovae. So the interesting thing down here, if you look at the blue, this is LIGO's best current rate for emerging neutron stars. That's 300 per gigaparsec cube per year. With a fairly large error bar, factor of 2 or so, a bit larger than a factor of 2, in fact. And so it's still, our upper limits are still not yet, they're perfectly compatible with the LIGO Virgo gravitational wave rates for emerging neutron stars. So our rates here are in green. The Atlas rate is less than 1,500 per year. So we hope, now this was made, Owen finished his PhD thesis and submitted it at the start of this year. So we've another probably nearly 10 months to add to this. So I would say by the end of the year, we're probably going to be pushing down into the upper limit of the LIGO rate. So I think certainly by the end of next year, we will be able to either find an object or constrain it to lower than the upper limit, the upper error bar in LIGO. And that's interesting. It's interesting, not just what are the rates of gravitational wave signatures, but what are the rates of these optical counterparts? Because all of the interesting physics, or not all of it, but a lot of the interesting physics comes when you identify the electromagnetic signature. Lots of interesting physics from the gravitational wave detections only, but there is so much more you can do when you identify the electromagnetic counterpart. So there are various other, in green here, lots of optical estimates of upper limits for kilonovae. In pink, there are the limits from short GRBs. Again, none of these are fairly compatible with the LIGO rates from the gravitational wave detectors. And so I think we're not looking at, to give you an idea, that 300 per gigaparsec cube per year means 1 every year within 100 megaparsecs. So all sky. So they're clearly not. During 03, the question was it 1 per month or 1 per year? And I think within 100 megaparsecs. And I think we know now it's probably 1 per year rather than the high rate of 1 per month. But at that rate, it's still worth searching for these. No, we have not found a case for emerging neutron stars, but I want to show you one example where we have found a very fast declining transient, which we think was emerging compact object, a white dwarf with either a neutron star or a black hole, but not neutron stars. So this one, 2018 KZR, we discovered this with jointly with Atlas and ZTF processing. We saw it rise rapidly. So the picture in the top left is our force photometry at discovery. So this object, here's the transient and its host galaxy. We perform difference imaging. So when there's no object, it should sit at 0 flux, which you can see here for 4 epochs. And then ZTF in its G and R band and the Atlas orange bands are shown here as detections, and then it faded very rapidly. So we saw this fading quickly, and we triggered many telescopes to look at it. It was very luminous, so it declined at a rate of 0.5 mag per day, which is much faster than supernovae, and close to the kilonova, close to 17 GFO. Although it was 2.5 magnitudes brighter than the kilonova, so much more luminous, but declining quite rapidly. So we followed it up with many telescopes. It peaked at 10 to the 43 ergs per second. And so the red points here are the data from 2018 KZR. The black is a simple model, a diffusion model based on the ICRANet formulation. And so it's got an ejecta mass of only about 0.1 solar masses, so more than the kilonova. But we can, so more massive than the kilonova, but still faded quite rapidly. This cannot be powered by normal radioactive decay because you can't get the peak and the decline rates with that. What we suggested was that you could have a spinning neutron star, and as it spins down, if it's magnetic and it spins down through magnetic dipole radiation, that causes magnetar type powering, and that we can reproduce the light curve with that type of powering. The powering source, that's just an analytical formula. It's a way of producing power on the time scales required to produce the light curve. It's not definitive that there was such a power source, but it shows that it's plausible. If you have a power source like this, it can reproduce both the peak luminosity and the decline rate. The white symbols here are another fast declining supernova, but you can see this event, 2018 KZR, was much faster than the fastest known supernova-like objects. So it's clearly lower mass and something more extreme than those. We don't think it's a core collapse supernova for that reason. We don't think it's a kilonova because when we took spectra of it, the composition of the spectra was, and so these are the spectra that we have here, and with some spectroscopic models, which were done by my student James Gillanders, who runs the TARDIS code, which reproduces the spectra with a composition. And he showed that it was mostly oxygen, magnesium, and silicon, with a significant amount of iron, but low amounts of nickel and cobalt. So the composition of iron is quite significant because we've got a very blue continuum with strong iron lines. So this doesn't look like, it's not kilonova type. It's not our process chemical elements. It's really compatible with being an oxygen, neon, magnesium white dwarf. The interesting thing is the iron lines are incredibly strong. And if it's iron, then it cannot be iron 56 because it takes a while for the radioactive nickel to decay to cobalt and then iron 56. It takes 6 days. The half-life of nickel 56 is 6 days. The half-life of cobalt is 77 days. But we detected these iron lines within 2 days or at peak, maybe a few days after explosion. So that tells us that it's probably iron 54. A different isotope to most of the iron in the universe, but stable iron 54. It's probably not radioactively produced iron 56. So this unusual composition, so overall it's a fast declining transient, an unusual composition. We suggest that the most likely explanation is that it's a merger of a neutron star and a white dwarf, or a white dwarf and a black hole. And there are several papers by Brian Metzger and collaborators that have produced chemical compositions of such a merger, and it's fairly similar to what we see. So particularly the one on the right, an oxygen neon white dwarf plus a black hole produces lots of oxygen, lots of silicon, and quite a lot of iron 54, which would agree with our composition. So I'll finish here. Summary is we've been searching for these fast declining transients. This shows you time scale versus luminosity. and the kilonova and these mergers fall to the left of normal supernovae. We're finding these unusual things which require powering sources that are probably not nickel 56. Stellar mergers appear like they're luminous, and they may well play a role in chemical enrichment. And I think there's great opportunity with future surveys to find more of these stellar mergers. Thank you.
Thank you very much. Very impressive talk. I have a questions. Maybe your opinion interesting for me. You know that now we see only one kilonova through the 3 observational sets of gravitational wave observation. Or 1, or 2, or 3, only one. And but sensitivity of the laser interferometer is very essentially grows. But no optical observation. What do you think about our how to say, our maybe soft for the searching of the kilonova on 300, 400 megaparsecs, very big volume. You see the first kilonova detected by the 5 telescope goes through the galaxy, 1, 2, 3, 4, to the list of galaxies. You remember?
Yes.
But now we have no list of galaxies on the 300 megaparsec. What is your opinion? What happened on the observation set 4?
So I think in 04, we hope they will be more sensitive, maybe out to 150, 200 megaparsecs. And so at that, it depends what, as you say, on the sky area that they produce. If they have 3 detectors, then the sky area will be small enough that many telescopes will be able to tile out the region. When they go beyond 200 megaparsecs, you're right that the sensitivity of our smaller telescopes will probably not pick up the kilonova, even if they're as bright as the one we've seen. So I think that's the era of LSST. Now, we hope that LSST, and there's a group lobbying the Rubin project to point the telescope at the gravitational wave maps and release the data publicly to everyone. So I think LSST is the next big jump. I think in 04, we'll still need some luck that we have one which is nearby enough that we can detect it with our smaller facilities, this sort of 50 centimeter to 1.5 meter telescopes. Then it's probably, if we don't detect anything in 04, I think we've got to wait for LSST, which is then 05, which will then be the 05 run. And we hope that the Rubin Observatory would carry out a survey for the public good and release the data publicly. And then everyone can search through it to find the data will be released by LSST publicly. That's a commitment they've made. We've just got to get them to decide to do it, to point the telescope in the right place.
Thank you. I understand you.
But I think in 04 we still have a chance.
I have not so optimistically to LSST. Maybe, yes, okay. But I think we have a lot of problem with soft of the optical transient searching. The number of transient is grows as a volume.
Yes. Of course.
And the number is big. A lot more telescope imaging, but they only have image as a 20th century. But
that's right.
Maybe we must maybe before we detected new neutron star measured like to 50, 70 megaparsecs from that's my opinion. Okay, that's very nice talk. Thank you very much. It's a very important question for the Professor Stephen Smart. Thank you, very nice. Next talker is Dmitry Fredericks from the Conus Wind team with very, very nice, important discovery of last years of the physics of radio bars and magnetars. Please, Dmitry. Hello? Yeah, we see your talk, but no voice. Dmitry.
Yeah, you're muted, Dmitry. You're muted on Zoom, bottom left.
Dmitry, please start it. Алло, Дмитрий.
Hello, can you hear me?
Начинайте. Мы все видим и ждем просто.
Вы слышите меня?
Да, теперь да. Yes, now we listen you.
Okay, my talk is devoted to the recent results on magnetar flares, especially giant magnetar flares, and their connections with gamma ray bursts and fast radio bursts. Magnetars, as you know, is a special class of neutron stars with very strong magnetic fields. Some of them, soft gamma repeaters, exhibit bursting emission in hard X-rays and gamma rays. In burst active phases, lasting from days to years, they emit numerous short, energetic, and soft bursts, different from classical gamma ray bursts. Much more rarely, an SGR may emit a giant flare, a very special flare, with sudden release of huge energy up to 10 to 46 degree. Initially, soft gamma repeaters were considered as a subclass of gamma ray bursts, but they're distinguished now from cosmological GRBs by the soft spectral and recurrent activity. Also, due to their energetics and high flaring activity, young magnetars have been supposed as the most promising candidates for progenitors of fast radio bursts and bright millisecond scale flashes of extragalactic origin. The year 2020 was a vintage year for magnetar science. There were two key results in this year. First is on magnetar giant flares, and an extremely bright short gamma ray burst was identified as the most significant candidate for, and the best studied candidate for an extragalactic giant flare in a nearby galaxy at about 3.5 megaparsecs. Another result is on magnetars and FRB connections. There was the first simultaneous detection of a fast radio burst and its hard X-ray counterpart from a galactic magnetar, SGR 1935 plus 2154. You see that there are plenty of papers on these events, but in this talk, I will focus on the Conus Wind and IPN results from these papers. Let's start with magnetar giant flares. Only dozens of gamma repeaters in our galaxy and LMC are known so far, but only 3 of them produced a giant flare. A typical picture of giant flare is a short hard spectrum initial pulse, which evolves into a softer spectrum long decaying tail modulated from the neutron star rotation period. The least studied studied phase of the giant flare is in the initial pulse. Huge photon fluxes in this pulse saturate. It reaches several million photons per centimeter square per second. We saturate almost all gamma ray detectors. Accordingly, the pulse structure, spectra, and energetics are reconstructed using indirect methods such as data from particle detectors or even reflection from the flare from the moon. All these methods results in very high uncertainties. Nevertheless, the initial pulse of the giant flare from SGR 1806-20 on December 27, 2004, both methods from particle detectors and from reflection from the moon resulted in a huge luminosity, which exceeds by 2 orders of magnitude the luminosity of the firstly detected giant flare on March 5 from Large Magellanic Cloud. It became clear that due to enormous luminosity in the initial pulse, giant flare can be detected from galaxies up to 10 megaparsecs away. It will be seen as somewhat untitled, short, hard GRB. In about 25 years of operation, Cornell's wind detected about 500 short gamma ray bursts, but up to recently, only 2 extragalactic giant flare candidates have been reported, both localized by interplanetary network. The first candidate, GRB 051103, was localized close to the M81, M82 group of galaxies at about 3.6 megaparsecs. At this distance, the huge flux in this flare results in 10 times more, even 10 times more luminosity that the SGR 1806 super flare. It drew concerns about that probably this burst is too luminous to be a giant flare. Probably it's background short gamma ray bursts. However, there were no gravitational wave detection that supports the idea of giant flare. On April 15, 2020, the bright short gamma ray burst was detected by 5 IPN spacecraft, and it was localized to a teeny area that overlaps the central region of the nearby galaxy NGC 253 at about 3.5 megaparsecs with a very teeny chance probability. The burst, interestingly, this burst is strikingly similar to the GRB 051103 in M81, M82 at nearly the same distance. Both have rise to peak, the millisecond scale rise to peak. There is now an initial spike and then gradually decay with a folding time of about 50 milliseconds. The duration of both bursts is about 150 milliseconds. Let's see the details of this burst. The light curves consist of 2 components: the very narrow, very short initial spike with rise time of about 2 milliseconds and with about 4 milliseconds. But the spectra of the initial spike are very similar for both bursts, with the peak energy of CCPL model of about 1.2 MeV, with the peak isotropic luminosity is also very similar for this burst and exceeds by a factor of 5 the luminosity of superflare from SGR 1806 minus 20. The slow component has gradually decays to the end of the burst with evolving times in count rate about 50 milliseconds, peak energy about 65 milliseconds, and flux about 30 milliseconds. The time integrated spectra of both bursts require two spectral components. The non-thermal component with peak energy is about 1 MeV and more than 2 MeV for the GRB 051103. And also there is a thermal component, weak, with the temperature of about 70 keV, and the radius of the black body very close to the radius of the neutron star is magnetic sphere. The total energy of the bursts differs about 5 times, and is on the order of magnitude with the SGR 1806 superflare. Black body contribution to the total fluence is about 10%, and the initial spike gives about 50% for GRB 2015 and about 10% for other. It should be noted that no similar bursts have been detected previously except the galactic giant flares, but the galactic giant flares do not demonstrate such a sharp spike. The initial spike of this burst was detected by Swift BAT and the Fermi GBM, and it shows a very variable structure on sub-millisecond scales, which never have been detected before due to the detector saturation. It's interesting. Another giant flare candidate from the Andromeda Galaxy, detected by Conus Wind in 2007, demonstrate similar variability, but on 10 times wider, longer time scales. In total, we have 7 giant flares and candidates, three from the local group, and 4 extragalactic magnetar giant flare candidates, all in star-forming galaxies within 5 megaseconds from us. They demonstrate complex white curves, but 2 of them discussed above are nearly clones. Probably they form a special class. However, the luminosities of the giant flares are up to 10 to 84 Ergs per second, which approaching the luminosities of some local low luminosity GRBs. Finally, the giant flare energy span 2 orders of magnitude, the probability density function slope of about 1.7, which is roughly consistent with recurrent SGR burst. But it should be noted that the slope was derived not accounting for schematics effect. Let's switch to magnetars and fast radio bursts. Up to April 2020, none of fast radio bursts have been detected in other wavelengths, and also there were no counterparts to numerous magnetar X-ray bursts. But on April 26, a bright 2 peaks millisecond scale burst was detected by 2 radio telescopes, CHIME FRB and STAR-2, from the direction of the galactic magnetar SGR 1935, which was in burst active period at that time. Simultaneously, a hard X-ray burst was detected by detectors in integral, agile, conus wind, and inside HMHC. 2 peaks in the conus wind light curves perfectly match 2 CHIME radio peaks that suggest the radio and X-ray emission have a common origin. Thus, this is the first simultaneous detection of an gamma ray or fast radio burst from a galactic magnetar and high energy counterpart. The conus wind spectrum of this burst is well described by cutoff power ρ with the slope of -0.07 and unusually hard peak energy. The total energy of the X-ray burst is about 10 to 40 degree Hertz. The ratio of radio and X-ray energies is about 10 to -5. It should be noted that the broadband spectrum, this is the approximation from X-ray to radio, is inconsistent with radio observations. The burst had typical fluences and power slope, but its peak energy of about 85 keV is the hardest for among all bursts detected from this magnetar ever. The emission is seen up to 500 keV. Interesting that no radio counterpart was found for about 100 typical for soft bursts from the same magnetar just after the April 28. This that's the idea that bright FRB-like signals are associated with rare hard spectrum X-ray bursts. This idea gains support from the burst statistics. Among 250 short SGR burst detected by conus wind from 6 burst prolific magnetars in 25 years, there are only 5 such hard spectrum events with peak energies above 60 keV. The burst rate, the rate of such bursts, about 1 burst in 25 years per active magnetar, appears consistent with the rate of SGR 1935 radio bursts derived from the CHIME observation. And here are some conclusions and speculations. GRB 200415 is the most significant and the best stated extragalactic magnetar giant flare candidates. Also, this burst is nearly a clone of historically the first MGF candidate in the galaxy group at nearly the same distance. The flares show similar spectral and temporal behavior, but the LCs are slightly different from other giant flare candidates. Both flares are superluminous, so probably this similarity is a special property of the brightest magnet of giant flares. The first detection of the bright double peak radio burst from galactic magnetar and its X-ray counterpart provided the direct evidence that FRBs might FRBs may be produced by magnetars. The burst peculiarity has peculiarly hard X-ray spectrum and simultaneously no radio counterparts to typical soft gamma repeater flares were found. This is the idea that bright FRB-like signals from magnetars are associated with very hard spectrum X-ray bursts. And this idea is supported by the hard X-ray flare and FRB statistics. Thank you.
Thank you very much. Thank you very much. And questions, I have one questions. Firstly, questions and some remarks. And my questions, what do you think about the, you remember, of course, the last year, April, soft gamma repeater and fast radio bars, you discussed it in your talk. And we, at that time, we observed by our telescopes this soft gamma repeater in 28 April. And we detected about 20 synchronous optical observation of the gamma ray flyers. Well, you remember there are a lot of flyers before the radio bars. As I know, all of them not give the fast radio bars counterpart, because, and I discussed it with some people from your team, and my questions, we see from soft gamma repeater, we see about 100 pulse of gamma ray bars, maybe several dozen, okay? But only one correspond to have the radio, fast radio bars counterpart. What is the differences between this pulse and another pulse in spectrum, for example?
I say that this burst is unusually hard. It's probably not so fluent, but it's about 10 to minus 6 ergs per centimeter square, typically. But the spectrum is very hard. It seems that it's not belongs to the general population of.
Okay. And you detected only one such type gamma ray, or not?
Only one from this magnetar, but
okay, I see.
But six such bursts from 6 magnetars for 25 years. Unfortunately, there were no radio observations of other.
Okay, I understand. Yeah, grazie. And is there any question? Because I have only a small remark. People. Okay, very nice talk, very nice, impressive detection of the all sky gamma ray detectors. Konus is very nice equipment, which several dozen years give us very beautiful discoveries and very simple, more or less simple space experiment. Okay. And I would like to stress that the phenomena of the fast radio bars was predicted in our institute in 1995, 20 years ago. 10 years before, 7 years before the Lorimer discovery, we predicted the short millisecond fast radio bars. But we predicted this radio bars as a result of the merging of neutron stars, magnetized neutron stars, as a precursor of merging. And in this, my questions, what do you think about the population of fast radio bars? Do you believe that the two populations, the unique and repeaters, or not? What do you think? Because the merging give only one only one fast radio burst.
This radio burst is from our galaxy. This is the first burst, but it's probably different from cosmological or extragalactic fast radio burst because
of course,
unfortunately, we can't see short SGR bursts from even from nearby galaxies.
Yeah, I see. I understand you. And yes.
So probably high sensitivity observations of nearby galaxies might give sound.
I understand you. Yes, the same problem with the gamma ray detection from the gravitational wave events, which distance is more than 200 and 100 megaparsec. I understand. Okay, thank you very much. You have the last word if you want. You have last word. No problem. Dmitry, thank you very much. Very nice.
Thank you.
Very nice
discussion.
Very nice discoveries. Okay, next talker is Sergei Svertilov. That is another Russian team which works in the gamma ray detector, observational detectors, astronomy, and one of the leader of the Moscow University team of the gamma ray detector on the different satellites. Okay, Sergey, can you start it?
I can, but it is necessary to close previous presentation.
Okay, close, Dmitry, close this presentation.
I don't know how to do it.
I don't know.
Put stop presentation.
On the top of your shield, you have leave the presentation.
Okay, no. Дмитрий, как это закрыть, ребята?
Там опция есть, закрыть презентацию.
Окей. Сергей, можете начинать. Oh, very nice.
Do you see my presentation?
Yes.
Yes, okay. I would speak about a new project of Moscow University, so-called Universitat Socrat project, among the goals of which observations of gamma ray bursts also. And this project is intended mainly for real-time observations of potentially dangerous phenomena in the near-Earth space with the use of the group of satellites. Among such phenomena, there are radiation, of course, and potentially dangerous bodies of nature and man-made origin, such as asteroids, meteors, and space debris, and of course, electromagnetic transients. And first of all, I would say a few words in memory of great scientist, Professor Mikhail Panasyuk, who was the owner and scientific leader of this project, and suddenly he left us, untimely left us at the end of the last year due to COVID disease. And of course, among the purposes of this project, study of electromagnetic transients, which include electromagnetic transients of astrophysical origin, such as gamma ray bursts, also they should be studied in this project. And idea is to create, to elaborate a group or maybe a system of several satellites. In minimal variant, there should be three satellites. One of them, the satellite of medium class with a payload mass about 1.5 kilos, which should be launched on the low orbit with the height about, with altitude about 500 kilometers, and also maybe 2 or more microsatellites with payload mass about several dozens of kilos, which should be launched on different orbits. And among these satellites, this group should be added by a number of nanosatellites of CubeSat type. And just these satellites can be used for GRB observation. And motivation for this is the very great success with simultaneous observation of well-known event in 2017, in 17 August, about which we also hear in our session. It is the gravitation wave event and the kilonova. It is the result of simultaneous detection of gravitation wave and gamma ray burst, the great discovery in physics due to these observations. And for multi-channel observation, it is necessary to realize the all sky coverage by gamma ray detectors. Just now, we have a few special observatories, orbital observatories for GRB study. Of course, it is Integral, Fermi, Swift, and of course Conus Wind, but they all are very, how to say, rather old. They have many, they operated in space during many years, and we need new observations. But just nanosatellites and CubeSat give us a good opportunity to realize such relatively cheap all-sky coverage, because it is very, how to say, rather simple and cheap satellites which can be launched by bypass missions, and they not need special money, special resources, and can be realized by our own forces, by Moscow University, for example. Such a system of CubeSat satellites also can be used for localization of GRB source by triangulation technique, and due to fast response can be used effectively for simultaneous observations with ground observatories, with ground instruments, as gravitation wave antenna, as neutrino detectors, cosmic rays detectors, and ground gamma ray telescopes, and other telescopes. Of course, there are some specific requirements to satellites which should be used for such observations. First of all, it is the necessity of satellite internet, because we need a real-time response, and we need to transfer to the Earth the information of about detected event. Also, these satellites should provide quite enough stabilization, no worse than 1 degree per second, special satellite orientation, and information about satellite axis orientation. Also, such instruments can be used for so-called quasi-astronomous navigation. It is a bypass goal, and use the pulsars as beacons. And different data types as monitoring as event by event, and telegram about bar triggers should be generated by such satellites. They also should provide a rather large volume of transmitted data about detected events, more than 100 megabytes. And I especially should emphasize the necessity of charge particle variation control, because we have a great experience in our previous experiment, so-called Lomonosov mission, about which Professor Lipunov also told in his presentation. And during this mission, we detect many GLBs, but also many events which caused by electron precipitation, electron flux variations, and the number of triggers which can be seen from this plot. The number of triggers caused by electron flux variation more than an order exceeds the number of real triggers from GLBs. And it is the problem for GLB observation, how to optimize triggers and how to exclude the events caused by variations of accompanying charge particle fluxes. And thus the constellation of satellites which can be realized by in the most simple way by CubeSats, if such constellation will be operated as a single instrument, it allows to solve the critical problems for such multi-channel observations. In particular, inter-satellite link of such system allows rise up the signal noise ratio. I should emphasize that SNR acronym, it is not a supernova remnant, but it is the signal noise ratio, because such system allow to detect one event by several instruments displaced in the space, and the problem of emission by electrons precipitation can be solved by such constellation. Also, constellation allow to localize the source by the triangulation technique, and the use the saved downlink also provide to realize the fast transmission of detected event on the ground and on the GCN network. What about detector? Of course, it is necessary to elaborate a specific detector for such compact and very small spacecrafts. And detector should have area no less than about 100, maybe a little bit less square centimeter. Very good time accuracy, and also such detectors should provide the wide dynamic range. It allows to detect not only the astrophysical events such as GLBs and bursts from source gamma ray repeaters, but also so-called terrestrial gamma ray flares, TGS. Study of such events also possible with the use of this system of spacecraft. And the first stage of realization of this project was began in 2019, when 3 CubeSats of 3U format were launched. And you can see here these satellites. It is very compact spacecraft. They were equipped by a universal instrument which we elaborated especially for CubeSat, so-called decor instrument. It is the acronym Detector of Cosmic Radiation. It is a pathfinder. Effective area of this instrument is rather small, about 20 square centimeter, 18 square centimeter. It is not enough to effectively detection of GRBs, but this instrument allows us to test the technique of detection and the realization of observation of gamma quanta and charge particle fluxes on board small satellites. You can see here how this instrument looked. It is a very compact instrument in compare with one page of paper. And it is the example of the data which we obtained from this instrument, from this spacecraft. It is the count rates in the channel of gamma quanta and electrons during one orbit. And we can use variation typical for near-Earth orbits, crossing due to, you can see some increases of count rates due to crossing of Earth radiation belt, the areas of precipitations, and so on. This picture demonstrates that instrument operates well, and really such detector can be used for detection of different kinds of space radiation. In September of last year, we launched 3 more satellites of CubeSat type. One of them is CubeSat of 1.5 unit and 2 of 6 unit format. They are also equipped by a decor instrument, and it is one of this satellite, how it looks. And you can see here the data from the satellite, so-called Norbit satellite, launched in September 2020. Also, it is the counts along one orbit, gamma quanta and electrons. And you can see here GRB-like event, how it looked, but it is not GRB, it is increasing due to precipitation of electrons, and it illustrates how it is why it is very necessary to control the variations of charged particles. Thus, we can say that we have tested the technique, and we can say that this instrument is quite useful for detection of different kinds of space radiation, and now we are ready to elaborate the special instrument for detection of GRBs. It should have the larger effective area, about 100 centimeter, more wide energy range, and this instrument we call so-called Decor 2. In optimal variant, it should consist from a number of small detectors, so-called pixels. Such a system allows us to separate effectively event from gamma quanta and electrons from one hand, and from the other hand, such system allow to exclude so-called pile-up effect due to reading data from each pixel. And in more simple variant, such detector can be realized as a PET detector, consisting from 4 detection crystals, and can be installed on the spacecraft in such a way that 2 variants of detector displacement, and they, how to say, such principle like in Conus experiment, well-known Conus experiment, when detectors have access directed in normal, usually normal directions, and likely form the Cartesian coordinate system. Such a combination of detectors allow us to estimate, roughly estimate, the GLB source position, even without triangulation. But the use of system of such detector also can realize more precise localization due to triangulation technique. And we plan to install such instrument in a number of CubeSats, which are planned to be launched at the end of this year and in next year. And we hope that the system of GLB observation by the number of CubeSats will be realized. Thank you for attention.
Thank you very much. Is there any questions? I'm sorry. Sergey,
Yes.
can I ask you about the real schedule of the nearest more weighty satellites?
It depends on realization, because we use so-called bypass missions, and we plan to launch the first satellite with our instrument, which will be able to detect GLBs with hope with enough efficiency. It should be bypass mission with so-called Meteor satellite. And it depends on our space agency where it will be ready to realize such launch. I think that really it will be in the beginning of the last second year, in the 2022, at the beginning.
Okay, thank you very much. Is there any no questions? We have to give the talk, the Nuria Jordana meetings, the role of magnetic fields in gamma ray bars outflow. Nuria, is there any, can you start?
Yeah, thank you. I still cannot share my screen now, I think, because there is Sergey.
Sergey, please.
Okay.
Oh,
Perfect, thank you.
Very nice.
Okay, so good morning. My name is Nuria Jordana. Maybe I will put the camera on. I will try. Okay, so good morning. My name is Nuria Jordana, and I'm a postdoc from the University of Bath. And today I will give a brief overview on the role of the magnetic fields in gamma ray borstat flows. Also, I would like to thank my collaborators that you can see here below, that they have greatly helped me and contributed to the work I'm going to present. They are from the Liverpool Telescope team and also from the Master Global Robotic Net collaboration, in which Professor Vladimir Liponov is also part, is the PI. So basically, this is the outline. I will start with what are GRBs, how are they detected, and also I will give a brief insight on the state of the art of the GRB polarization observations and how early time polarization can distinguish between magnetized and baryonic jet models. Then I will move to this very interesting GRB, which was GRB 190114C, which was one of the most energetic GRBs detected, and also the first one to be detected by MAGIC in the 10 electron volt domain. However, these observations contrast with previous observations of highly polarized GRBs at early times, and the polarization was very low seconds after the burst. Also, later on, I will also mention the GRB 141220A, in which we have published recently. And it is also very interesting because we can constrain the polarization of forward shocks at very early times, which also gives some insights on the magnetic field amplification mechanism at the front shock. So what are GRBs? GRBs are basically the brightest flashes of gamma rays in the universe, and they are formed when an extragalactic massive star collapses, or there is the merger of two compact objects such as neutron star binaries or neutron star black hole. Then the accretion onto this newborn compact object, such as a black hole or a magnetar, powers two ultra-relativistic jets that burrow through the stellar envelope, producing the characteristic gamma ray prong that we observe. This characteristic gamma ray prompt, there is two main competing mechanisms. It is internal or magnetic dissipation mechanisms. So the first one, internal dissipation mechanisms, they are basically internal shocks. So these internal shocks are produced when shells of different velocities are ejected from the central engine, colliding and releasing kinetic energy. In contrast, the magnetic dissipation mechanism, this can be something as reconnection. And then when this outflows collides with the interstellar medium and gets decelerated, this produces the characteristic and lingering emission that we see afterwards, called the afterglow. The afterglow is produced by these two shocks, a pair of shocks, a reverse shock that propagates backwards into the jet, and a shock that propagates into the interstellar medium. A key point here, and that I will mention later, is that the reverse shock still has the properties of the central engine, and the forward shock has the properties of the ambient medium, because it's basically shocked ambient medium. So how are they detected? These GRBs are detected because basically they are pointing towards us. So we don't see the jet edge on, but face on. And we also detect them as it has been seen in this parallel session, and with these gamma ray telescopes. So the gamma ray telescopes, they detect them because it basically outshines any source of gamma rays in the universe. As you can see here in the middle cartoon, you can see here that it outshines like Milky Way emissions, such as things like that. And then what we have after this is that thanks to real-time alerts, there is a campaign of small, intermediate, and large telescopes. What is interesting here, as you can see on the left, is that if you want to access the optical prompt and reverse shock, which is fast fading and only lasts seconds to minutes after the burst, we need these small and intermediate robotic telescopes that do not need human intervention, such as the Master Global Robotic Net or the Liverpool telescope. Like in case we wanted to study the forward shock, this will require large telescopes because the emission fades. And also there is the handicap of the manual trick of observations. Here on the right, you can see how we will detect a GRB here, like in real life, which is basically a point source. It's not, we don't see the jet, and it's basically unresolved. So it's a dot that gets brighter and then fades away. So what is interesting, apart from the spectral and temporal properties of the GRBs, is the polarization of the light. So the polarization of the light provides a direct proof of the structure of the magnetic fields within the emission region. And this is interesting because we know that the emission mechanism is synchrotron. Synchrotron radiation is 70% polarized intrinsically. This is in the lab. However, in these relativistic jets, if there is a large-scale magnetic field, this will be further reduced to 50% due to relativistic aberration mechanism. Also, if there is distortion of the magnetic fields or there's overlapping of different emission components with different polarization properties, this will get further reduced to basically zero if the magnetic field is completely taken. So what the start of the field of the polarization observations was in the 90s. And during that time, they measured 1-3% polarization for the forward shock. This 1-3% is due basically to a break of the symmetry in the emitting region, and it's basically attributed to the large-scale geometry of the jet, and also induced by the dust surrounding the ambient medium if it's basically a very obscure environment. Then the main model at that time was the baryonic model, in which this model, like the magnetic fields do not play a dynamical role, and the baryonic energy dominates over the magnetic. However, they also exist, these magnetized jet models, in addition to this baryonic model, and the jet could have ordered magnetic fields ejected from the central black hole. And then polarization observations at early times can potentially help a lot in distinguish between them. That is because baryonic models, the early time emission will not be polarized, but in the case of the magnetized models, there will be highly degrees of polarization expected, like in the sense of 50%, not 70 because it's the maximum allowed by synchrotron, but 50-30% is what we will expect at these early stages. Then also there is some differences here. So there's the mildly magnetized jet in which the prompt and reverse shock is polarized, and prompt is still understood as internal shocks, but also there is a highly magnetized jet, and in this case, only the prompt is polarized, and the reverse shock is not that significantly polarized, because during the prompt, there is this magnetic reconnection that breaks the lines and causes the complete destruction of the order of the magnetic fields in the outflow. So basically the state of the art of polarization observations point toward these mildly magnetized jets, because we have seen, that that basically prompt and reverse shock, as you can see here on the left, are polarized. So we have seen this 30-10% polarization degrees for reverse shock, and this points towards this intermediate stage in which magnetic fields do not actually play an important role later on for forward and reverse shock, but they still exist and jets are launch magnetized. Linking with this jet physics, we have the case of GRB 190114C. So this case was, as I said, it was very interesting because basically it was one of the most energetic GRBs ever detected. And it was interesting also because we got data from Master Global Robotic Net as soon as 30 seconds after the burst. You can see here in the white one. Then additionally to this, we also got data from 50 seconds after the burst, and thanks to two sites responding simultaneously, as you can see here, one from Canary Islands and the other one from South Africa, we could gather polarization data from polarization degree and angles at the same time. So also, in addition to this Master Global Robotic Net data, we got data from the Liverpool telescope, which started 200 seconds after the burst. And it was interesting too, because we could gather photometry and polarimetry in 3 optical bands simultaneously, with resolution as high as 2.4 seconds after the burst. You can see here the data in this blue color. Also, it is interesting because as the bands are simultaneous, we can do a 3-point spectrofit, and we can derive the spectral slope of what's going on in this burst. Also, the polarization was very interesting because we showed an initial 8% detection with master, and then suddenly dropped with 2% level, and was constant for the rest of observations, with also constant angle. If we model the emission in terms of reverse and forward shock model, we can see the classical interplay between these two types of emission. So usually reverse shocks are meant to decay with a power law of -2, and then the forward shock starts to emerge around, in this case, 1,000 seconds with a power law decay of -1. So causing this kind of flattening that you can see here. Also, it is very interesting because fitting the model allowing for free fit on the peak time, you can see the evolution, the expected evolution from blue to red bands of the typical forward shock synchrotron frequencies crossing the bands. Additionally, the optical spectral index also shows this extra spectral component and is consistent with this need of the passage of a forward shock crossing the bands. So this picture is basically proof of this classical forward shock, reverse shock interaction. And then the question is why the reverse shock is not polarized during this transition, and why there is no this monotonic decay of polarization when there is the unpolarized forward shock emerging. So, and why we have this 8% and then sudden drop to 2%. So putting all the information together, here we can see in the bottom part the polarization, and in the upper part the flux. So if we model the emission in terms of this reverse forward shock, we can estimate by estimating the strength of reverse shock to the forward shock, we can estimate how magnetized was the original ejector, because as I said before, the reverse shock still is sensitive to the properties of the central engine. So we know here that the reverse shock was 70 times more polarized, more magnetized than the forward shock, and this evidences this existence of primordial magnetic fields ejected from the central engine. Also, from the polarization, we can estimate the structure of the magnetic field, and this 8%, well, 7.7 detection at prompt emission timescales is also proving this evidence of large-scale order magnetic fields in the firewall. So we are not in the situation of a baryonic jet. This 2% that we see here is dust. We estimate this is dust induced because if we model the spectral energy distribution, we see that the GRB was in a quite obscure environment. And then putting all this together, what we what we suggest here in this case is that we are not in the case of a mildly magnetized jet, but a highly magnetized jet. So the large-scale magnetic field was completely distorted at prompt emission, and there was magnetic dissipation mechanisms powering the gamma ray probe. So this is one of the first cases of this highly magnetized jet regime, maybe powering these bright explosions. Now in a total different topic, it's not about the jet physics, so it's completely different. Even if there is baryonic or magnetized jet, we are talking about the forward shock, which the forward shock basically here is this shock ambient medium, so the shock that propagates into the interstellar medium. So in this case, we have another problem, is that the forward shock model actually suggests these levels of magnetic energy density. However, the magnetic energy density of the interstellar medium is quite low, so it's like 6, maybe even 10 orders of magnitude smaller. So we need a kind of amplification mechanism of the magnetic field that cannot be accomplished just by shock compression alone. So there is this need of plasma instabilities or macroscopic turbulences. However, in both cases, the predictions are that forward shocks are not polarized because these instabilities do not produce enough large length scales so that it will produce like appreciable polarization at the times we're observing, even at very early times or during the prompt emission. So here we have observed that late times polarization studies, we measure 1–3%. However, as you can see here, there is this early time case of 10% detection for a forward light curve. So this was a very interesting case because it's against all predictions of theory, because forward shocks are meant to be unpolarized with these smaller length scales. But what they say here is that the macroscopic turbulences are macroscopic enough that they will produce big magnetic domains. So here enters this model that is called the patches model, in which each magnetic domain has 50% polarization. So the maximum load in this case, accounting for relativistic aberration effects and all this stuff. And because the emitting region is bigger than this, we will average out this polarization. So at the end, we will have, for example, in this case, 10% polarization. Then as the time goes on and the emitting region becomes bigger, these patches will average out and reducing the overall polarization. And also there will be polarization swings in the angle due to this process being stochastic. So at the end, we will have this kind of pattern. And what you can see here is that basically we will recover the levels that we see at late times. So basically this early time observation will not be completely incompatible with late times observation, and also marginally also compatible with this kind of also early time observations. So here you have this 10% detection and this other early time forward shock polarization. So here the science question that is very interesting is what happens here. So if we find a GRB with a forward shock light curve that is basically with a time closer to the burst than this one, will actually act like a microscope, and we will have a smaller emitting region, and then we will sample this regime here. So in this case, we will have maybe 15–20% polarization for a pure forward shock. So here enters this burst. This burst is a classical forward shock at early times. So it has the properties, spectral and temporal properties of late time forward shocks, but it starts as soon as 86 seconds in the observer frame. So in this model, the GRB should be 20% polarized. And it is very interesting because we find 2.8% polarization for the GRB. So actually the GRB proves theoretical expectations and not favors, in this case, this patches model. So in this paper, what we also discussed is the expected polarization of early times forward shocks. And we actually discussed polarization from the dust of the GRB environment, which in this case is also quite obscure. So we will fully account for this 2.8%. Also from the jet geometry, that basically these 2 points here are also can be also applicable to late time polarization studies. And in this case also, what is quite interesting is that there could be also contribution from a polarized reverse shock, which will allow for 10 and 30%. And actually, in this case, for the 10% forward shock light curve, it could be very possible that they were detecting a special reverse shock, like another line component of the reverse shock, or basically a long-lasting reverse shock that would also account for a kind of harder slope of the light curve, like mimicking a forward shock. And also what is interesting here is that actually it agrees with the magnetic field length scales from collisional shock, so from what theory predicts, which predicts this less than 2%. So in this case, it's interesting, as you can see, there's a burst that actually matches a little bit the theoretical expectations of GRBs. So here I finish my talk with this plot here on the right. As you can see here, there are all the relevant or more relevant polarization measurements of GRBs. And you can see that during the first minutes after the burst is when we can infer this jet physics, this baryonic magnetized jet model, in which baryonics we will not expect polarization, and magnetized jet we will expect polarization. So in this case, current observations, they favor this case of mildly magnetized jet, but also notice that there is this case of GRB 190114C, in which we believe it was launched highly magnetized. Also, I finish with this statement that now there is like these two bursts, and it seems that forward shocks are unpolarized as predicted by theory, and that GRB from 2009 that was a forward shock with 10% polarization, it could be a reverse shock. So many thanks, and if there is any questions, like I would gladly answer.
Спасибо. Все нормально. Сейчас, извините. I'm sorry. Okay. I'm sorry. Some form. Thank you very much. I have the one short question because we have no time for. Okay. I know that the main telescope, your Liverpool telescope, okay? And my questions, what is the main properties of the new polarimeter on your Liverpool telescope? What do you know?
Yeah, like the new polarimeter is called MOPTOP. So Ringo 3 was decommissioned, so now there is not 3 bands, there is 2 bands. And what is like 3 bands was great for photometry, but the problem is that for polarimetry, it greatly reduced the sensitivity. We cannot estimate as good like the polarimeter. So what is important here is the polarimeter. So now they have reduced to 2 bands, and the sensitivity has greatly improved in this case. So it has, we have this kind of change in this new polarimeter. So we hope to provide more sensitive observations of GRBs next time.
I know you have new data from the last week. Very nice GRB, not last 2 weeks, maybe.
Yeah.
Okay.
Yeah.
Okay. Thank you very much.
Thank you.
And okay, the last talk will presented by the very young our researcher from the Moscow State University, Kirill, very talented, Kirill Zhirkov. Kirill, you are ready?
Yes, I am ready.
Okay, you can start.
Okay. Hello, everyone. I am Kirill Zhirkov from Moscow State University, and I will be presenting optical perturbations of laser TXS 0506 plus 056 during the IceCube 170922A. You do see my presentation, right? You can hear me.
Yes, all okay, all okay.
Okay, that's great. So, IceCube 170922A, a famous high-energy neutrino event that was detected by the IceCube Neutrino Observatory on the 22nd of September 2017, and it is thought to be the first high-energy neutrino that was produced by the astrophysical source, a flaring blazar TXS 0506 plus 056. This connection produced a multitude of papers. The most notable one of them is a paper in the Science about the observations of this blazar. In this paper, they produced an interesting light curve based on the multi-messenger observations from the very high energy gamma ray data down to the radio frequencies. Here you can clearly see the variations in the very high energy gamma ray data, and the X-ray, while in the optical and the radio frequencies there are practically none. However, this connection between the neutrino and the blazar is quite slim. Chance coincidence probability is 3 sigma, which is quite low, and many could argue this is simply a coincidence. To clarify the connection between the neutrino and the blazar, you need a more observations on a more shorter time scale, preferably minutes after the event, that observe some unique event. Such observations were made by the Maestro Global Robotic Network. What is Maestro Global Robotic Network? It is a network of 8 40-centimeter K-dioptric paired telescopes with a 2-degree field of vision that are able to automatically respond to any alert 1 minute after the notice and observe it if they can. To IceCube 170922A responded 2 telescopes, Maestro Amur and Maestro Tavrida, but only one, Maestro Tavrida, was able to make proper frames for unknown reasons. It started the observations 73 seconds after the trigger and made 3 frames in the first 15 minutes and a total of 23 frames in the first 3 hours. It should be noted that the zenith distance at the start of the observations was 84 degrees, which is quite a lot. And here you can see a set of 3 frames. The left one was made approximately a week before the neutrino. The middle one was made 2 minutes after the neutrino, and the right one was made 2 hours after the neutrino. As you can clearly see, the blazar on the middle frame is significantly dimmer than on the left and on the right ones. And here you can see the amplitude of this difference, 0.8 magnitudes, and the blazar clearly underwent a significant optical decay immediately after the event. That was followed by a rebrightening to the past level 2 hours later. Here you can see the full optical history of the blazar made by Maestro telescopes over the years. And you can clearly see that during IceCube 170922A, blazar didn't drop to its absolute minimum ever, which is interesting. Now, what could have caused this optical decay? First and foremost, the decay is connected to the blazar and therefore to the neutrino production. Second, the decay is caused by the absorption in the atmosphere. After all, the distance was 84 degrees right after the event, and so it is not connected to the neutrino production. The only scenario verifiable with our data is the second, atmospheric absorption, so we checked it. Here you can see the magnitude variations of differently colored stars and the blazar. On the upper part of the figure, you can see check stars with different colors. Colors were taken from one star's DR1 catalog. The reddest one has the color of G-R 1.25, while the bluest one has G-R minus 0.79. And you can clearly see that the blazar brightened too much for it to be explained by the atmospheric absorption. Of course, if its spectrum didn't change extremely, which is extreme, it is extremely unlikely for it to happen. So, if the decay was really connected to the blazar, what can it tell us? Well, this decay could be explained quite easily if we assume that the optical emission is mostly produced in proton synchrotron emission model. If half of our proton generating optical emission turned into neutrinos, then we could expect a drop in optical flux by a factor of 2, which we do observe. However, this model contradicts very high energy gamma ray data that hints towards leptohadronic emission models. You can read about in these papers. This decay puts an upper limit on the neutrino production zone size it is several light days for a Lorentz factor of 5. And interestingly enough, a similar effect is seen in very high energy gamma ray data, where magic telescopes observe rapid rebrightenings after the several days of Plato. Results. TXS 0506 plus 056 underwent a significant optical decay during IceCube 170922A and rebrightened 2 hours later. The amplitude of this rebrightening was 0.8 magnitudes. This decay can't be explained by atmospheric absorption if a blazar spectrum doesn't change extremely. Similar effects on a different timescale is seen in very high energy gamma ray data. And the neutrino production size zone doesn't span for more than several light days. Thank you for your attention.
Thank you very much. Very nice talk. And is there any question, people, for the young scientist?
Yes, so Stephen here. So you saw this you just saw this in the dip in one of the master telescopes, is that correct?
Yes.
And it's at 84 degrees zenith distance.
Yes.
But I mean, I was quite convinced with your plot of the comparison stars that they look pretty secure, that there's no variation. I mean, that's a huge drop. What was the next observation you got after 3 hours? Did it return
after 3 hours? Our observations continue on the 3rd day, if I remember correctly.
Okay, and then it's back to normal.
Here. Yes, it is normal.
Wow. Okay. So is it? That's a huge drop.
Yes,
it looks very. I mean, it does look very convincing. So are you saying you haven't seen such a drop as in a similar time scale in the history of this object?
No, but our observation doesn't cover this short time scales. We usually observe one in the several days, so it is hard for us to observe such an event.
Okay, I see. Yeah.
Okay, next questions. I have questions, Kirill, okay. from the neighbor. My questions is, did you analyze it, another such type of neutrino follow-up optical neutrino observation by Master? How many observations, Master? And where is this published? You not give us.
Well, Maestro does observe such events. We observe around 1/3 of them in the first 2 hours, but unfortunately, our observations don't cover most of the error boxes, and only 8 blazars were observed before 2 alerts in 2 hours after the alert. Yes.
Several alerts. Now,
yes.
And you plan to publish it in future, maybe.
Yes.
Okay.
I do plan.
Okay. And I would like to note that Master, during the last 5 years, observed about 300 or 400 neutrino events from 3 neutrino detector from IceCube, Antares, and Russian Baksan equipment. And but Baksan equipment is not very high energy neutrino. Okay, and this observation is very complicated because there is a lot of coincidence of the weather, distance, and so. But we have about 10 observations. Unfortunately, Antares observation, we cannot publish it. But I would like to say that a lot of maybe neutrino alerts is not real. Not real astrophysics.
Yeah.
Maybe. We do not know. We must analyze it. Okay. If you have some discussion, a small opinion, because we come to finish of our session. Is there anybody to say something? No? Okay, dear colleagues.
I think another point for Kirill. So I think just another point for Kirill. You could go to the Atlas survey data and you can pull out the historic light curve for this object to see if there's any similar dips. We observe 4 times per night every 2 nights, and so those data are publicly available, and I can help you. I can point you in the right direction to do that, just to see if there's any similar drop. I mean, I think for this object, I was never fully convinced that any of the other electromagnetic signals were well, they weren't temporally coincident with the neutrino, but this obviously is. This is a standout where it actually is temporally coincident. But I think looking for any sort of variation that repeats on that time scale in the Atlas data might help you, and certainly would help strengthen the argument that it might be related to the neutrino.
Yes.
And just a moment, Kirill, show the last right side of light curve. You see this, we especially observed several hours this blazar in the usual state. You see no change more than several, so no changing during the several nights.
Yeah.
So of course needs the next observation, because there's only new paper last year in the physics journal Letters, only one such type of observation. But we, Kirill, what do you think about the importance of such observation in future?
Well, it is important, and it will be interesting to find another events for other blazars coincident with high energy neutrinos. And in Texas.
Yeah.
No, that's all.
Okay. Okay, dear colleagues, many thanks for your participation in our section, which you have decorated with excellent reports. I want to wish you new discoveries and course health. I believe that in coming year, new surprise await us in the universe of relativistic stuff. Since see you soon. Bye.
Thank you.
Many thanks.
Thank you very much.
Bye-bye.
Thank you. Bye.
Bye to everybody.
Bye. Thank you.
Ciao.
Right.
Bye, Vladimir.
Ciao. I hope to see you this
I
year.
hope to, yeah, maybe next May.
Okay.